Okay, brilliant. So, hello everyone. My name's Joseph Anson, and today we're going to be talking about beyond type checking and how we can build truly bulletproof TypeScript applications. So in this talk, we're going to be looking at the problem with compile time safety from TypeScript, and we'll be also looking at potential runtime solutions for this, runtime validation. We'll be looking at some real-world examples, and then finally we'll be looking at some the ecosystem and the tools that the runtime validation supports, as well as some adoption strategies for your applications. So firstly, we have to start from the beginning, and let's look at the type safety journey from JavaScript. And I believe it's broken into 3 succinct phases. So the first phase is the JavaScript era, the initial trust me era, where nothing was typed, anything could be anything. If an object was called user, it was, until it wasn't. And then along came TypeScript. And finally, we could add types to our applications, and we could type different, we could know for certain if a certain object was typed in a certain way that it had these certain properties. However, now we fit in a third phase, which is now the runtime safety gap. So where did things go wrong? Well, unfortunately, the vanishing act of TypeScript is that all our TypeScript types get removed when the application is compiled. So we no longer have any type safety with real-world application data. Secondly, there's an illusion around APIs, and we always kind of believe that APIs return the data that we're expecting. And very often they don't, and this will lead to a lot of styling errors in your applications. And thirdly, with TypeScript, we have an overuse of the as keyword, or using, for instance, generics to kind of set data coming into our application. So whether this is API requests or form data and the like, this can also lead to errors within our application. So I like to think of this in the way of a trust boundary. So let's first look at how, in JavaScript, we have this is how JavaScript looks, where we have a user, and this is just a user purely because it's named user. We don't really know what properties are on there. I don't know how people develop in this way. But then we introduce TypeScript, and finally we're able to describe our objects, and now we know it is a user and it has an ID and a name on it. However, this kind of falls a bit short, because whenever we do something like an API request, where we're fetching the user, we're getting the response.json, very often we just say, hey, TypeScript, trust me, this is this type, just believe me. And the same when we handle session storage, or when we go to local storage. We just set our local session storage, and again, when we want to retrieve that, we just say, hey, TypeScript, trust me. And we do this in many places, like getting query parameters, or environment variables, where we say, hey, just trust it there, or the file system, or even when we handle form data, where we might be using a library, such as, in this case, we say, yeah, just trust me, and we pass in the generic of user, and then this form is going to generate that type. So very quickly, you can see that we haven't quite moved on from the JavaScript trust me era, and we're saying to TypeScript in a lot of places, hey, just trust me. This is what it is. So why does this matter? Well, the cost of assumptions can be very costly, and mismatched data can often lead to crashes and corrupted state within our application, and debugging becomes incredibly difficult. We end up with this illusion of safety, where compile time safety doesn't equal runtime safety. Just because in our application we say it's something, very often it doesn't end up being. And thirdly, why it's important to think of this trust boundary is that we have full control of how we trust the data flow into our application, and we should be validating all the data and everything that comes into our application to ensure that it doesn't cause any damage to our application in the long run, whether that's via corrupted state, or maybe setting data within the store. So I'm going to give you a short example here of the runtime validation gap. And this is actually from an application I've been working on at my current client. And we'd been building a loan application. So the whole idea was the user would come, they would fill in their incomes, their expenses, and eventually they would be told, hey, whether they've been approved for this loan, or declined, or in this case, a manual review. And they'd be told what interest rates they got and the total amount. But what ended up happening for us was we would query the API, and the API sometimes, only sometimes, would return undefined. Now, our application and our TypeScript code, we were told this is required, this will be there. And our backend schemas, they were also telling us this is required, it's impossible, of course the loan status is going to be there. But because we had runtime checking and runtime validation, we were quickly able to identify, hey, some of our users, this isn't available. So in the end, we asked our testers to mimic the same response, have it undefined, and we found out that our application was crashing. The user was getting no indication. There was no message to the user. It was still a 200 status, so technically it was a correct request. However, it was breaking. So we notified our backend teams. They looked into it, and yeah, it turns out it was like a downstream error. So one backend was calling another backend, that was calling another backend, and somewhere along there, we were losing the loan status. So the real world impact of these issues is, yeah, you can lose a lot of money. These bugs are very costly, and they can have a very direct financial impact on your application. You can have a significant debugging time, especially with these data-related issues, because you don't know for which specific user that this is happening for. There can be a massive degrading in user experience. In the case of the loan application, the users just filled out this long form, and suddenly they've gotten nothing for their amount of work. And thirdly, these issues are incredibly hard to reproduce. Often when you're using your user data, you can't just freely access it, so some of these data issues you can't easily access. So we'll have a look at another example of some runtime issues here. So we're doing a fetch call. The fetch call comes back, and it turns out, again, the data is a bit wrong. So in this case, it's a bit extreme. But just to give some runtime examples of how it could crash your application. So in the case of age, we're expecting a number, it returns a string. So we're doing this comparison here. It's not going to work because it's comparing against a number. Again, with the role, we could be checking for admin, so just to show admin UI to certain roles. However, we're not considering the guest. And then thirdly, because isActive is a string, it's always going to return true. So these kind of data-related issues can really drastically affect the way your application is running. So how do we take our applications from blind faith to bulletproof validation? And how do we build trust by doing runtime validation? Well, let's start with what runtime validation is. So runtime validation is the validation of data types or structures within your application at runtime. It will provide external guards to your application, so any kind of data coming into your application, or any kind of database result, or any kind of user input. And then, and lastly, which I find the most important, is it will give us very quick and early warnings. So we can quickly identify the issues with the data coming into our application, and we can rectify the mistake and rectify these or adjust our application to support them. So there's 3 main libraries out there at the moment which handle runtime validation. There's Zod, Valleybot, Archetype. There are other ones that exist, such as Joy or Yup. The first 3 libraries have just worked together to create something called the standard schema. The standard schema has just reached version 1. What is the standard schema? Well, the standard schema is a collaborative effort, so it's a unified standard across all the validation libraries. So you can approach schema validation in a unified way. It's a collaborative initiative between Zod, Valleybot, and Archetype. It allows for easy ecosystem integration. So if you're creating a library or you want to support schema validation within your library, if you support the standard schema, then all of these libraries will automatically be supported. So you just support the one interface, and then the libraries that all support standard schema will also be supported. And by being a community-driven, it'll be based on real-world implementation. So in the rest of this talk, I'm going to be talking primarily about Zod. However, there are as I mentioned, the other 2 libraries are perfectly valid for these kind of use cases. But in my case, I'm going to be talking about it because it is the most popular. It does give you a very easy way of inferring types from your schemas. It has a great developer experience, a very good documentation, has a very rich ecosystem, so this is one of the first, so the ecosystem has a lot of libraries that support it, and not necessarily other libraries just yet. And it provides a lot of functionality. So not only does it do validation, it also allows you to do data transformations and generate data and much more. Sorry, quick drink. Okay. So what are the essentials of Zod? Well, Zod provides a utility that you can export from the Zod library. So in this case, it's a Z object. And on that Z object, you get a bunch of types. So I don't have the full extensive list here. There is more. So with each one of these, it will cover basically one of the types within JavaScript. So whether it's a string, or an array, or some kind of Boolean. And the cool thing about Zod is that you can easily add on additional validation. So you can say, in the first case, I want a string. I want it to be an email. I maybe want to trim off the extra white spaces from the string. I want to check that a number's positive, and maybe it has a multiple of 5. So you can do these nice kind of like validations on your data as well as when it comes into your application to verify, okay, we want an array, maybe we want at least one item in the array minimum, otherwise we can also flag that to our backend. How you define schemas is, in this case, this is probably the most common, is you define, in this case, you define an object, so a z.object, and within there you just define your properties. So this looks very similar if you're used to creating TypeScript types, and then you can validate again with the additional validations. So one of the main things that, and the main benefits of Zod and these schema validation libraries is that you can infer the types. So with this, you just define a schema, and then with the schema, you can infer the type using z.infer, and then you get the type free. So in this case, instead of writing all your TypeScript types, you can just write the schema and insert the type for free, which is super good. So how does validation work in Zod? Well, validation has two flavors within Zod. There's parsing. So parsing allows you to, in this case, we have the user schema. We can do .parse on the user schema, parse in the data, and then if it successfully passes, we now get a data type that is of user. So in this case, it automatically infers the type to us to result. So we don't have to add any types there whatsoever. We get the type for free. And in this case, if it does fail, it'll throw an error. So in this case, we catch it, and then we can log it out to our analytics, or however you want to handle that error case. It's very often that if corrupted data comes to your application, you kind of want to just error out, because it's not going to handle it correctly, it's not going to work well, it's not going to use it correctly, so it's best probably to error out. The second way of doing it is to do safe pass. This will not throw an error, but instead it will return a result, and this is the result pattern. So if it's successful, so if success is true, it's going to give you the data. If it's false, it's going to give you the error. So this enforces you in TypeScript to check if it's successful. So we're always checking if the data is successful. So in this case, if the data is not successful, we log it, and we can return out early, or because we've already handled the success case, so in this case success is true, we get the data. And as you can see in both instances, we're not having to do anything with TypeScript here, it's just JavaScript, and we're getting the types inferred automatically. So how does Zod work in practice? Well, here's a quick example. So we have our recipe here with a title of string and a cooking time of number. But as you can see, as we're doing the parse here, the data inside our parse is incorrect. So we're having a string. So Zod will inform us of this. So we're seeing below, we have a console log, and it's saying success is false, and it's explaining to us the issues. So it's saying that the code for this issue is an invalid type. It's not the correct type. It was expecting a number, but it's received a string. And the great thing about this is it tells us exactly where it's expecting it. So it's saying the path, which is the key, is cooking time, and this is where it's happening. So if you're using this in a data-sensitive application, it's not informing you what the data is. Oh, this is the incorrect data. In fact, it's telling you just where the property is and why the type is incorrect. So if you want to debug this, in our case, we use it at the bank, and it works incredibly well. So it doesn't leak any personal information, but it does tell us exactly where these issues are happening. So if we were to correct that now, and we were to change it, then we see that success is true, and then it's going to give us the data. And that data then is going to be typed correctly against the schema. Right now, the examples are quite simple with an object, but you can do arrays. And if you do an array, it'll tell you, OK, array index 0, and it's this property. So quite quickly, it'll tell you exactly in which part of the array it's going to flag, the issue is going to be flagged. So Zod in practice. So if many people here are TypeScript developers, you're quite used to writing your types like so. But what you can do instead is you can create a schema, which mimics almost exactly the same shape as your type. And instead, you can just infer it. Sorry, one before. We can add some additional validations here for free. So now we can also, not only do we get the type, we can also add some additional validations. And then we get to infer the type for free. So instead of writing your types, you can just write schemas. So you just write your schema, and then you can use these to validate different parts in your application, infer the type, and then essentially you can use that type just as you would anywhere in your application like you would have used the type before. So in this case, I have a quick example. We're going to fetch a product. So in this case, we can now use the type we just inferred, and we say it's going to return a promise of product. We're going to do our fetch, and in this case, it's the old way, right? Like we're just saying, hey, this JSON response is a product. Well, actually, we can quickly improve that with one line, and we can say, OK, we don't know what's going to come into our API, but we are going to validate it with our product schema. So in this case, we're going to do the safe pass. This is my personal preference, but it's completely up to you. And then we can quickly check. So we can say, OK, if that API isn't successful, or if we don't get the correct data to our API, let's log it. And then we can maybe throw an error, so we can error out in that way. And then finally, if it is correct, we can return it. So now our fetch function will return the type of product. So now you can see how just by creating the schema, we get like almost free, the type for free. It's almost only maybe 2 more lines of code, and we get full-time runtime validation. The very cool thing about this is that if we do change the schema, it's going to update our type. That's going to update the way the API works. So we end up with like one source of truth. So by doing schema-driven types, we can automatically, sorry, I kind of jumped ahead there, but we can automatically infer using the z.infer. We end up with a single source of truth. So the schema, if we change the schema, it automatically reflects in all our TypeScript code across our application. And then we end up using it's quite a common one, the dry principle, where it eliminates duplication between runtime validation and our type declarations. So this is, I think, one of the most powerful things of Zod. And schema generation in general. So now we've looked at the basics of how you can use Zod and schemas. Now we're going to look at a bit more advanced types, ways of using them, and a bit more use cases. So we'll create our reusable user schema. And then the first, what we're going to use that same schema to handle our form validation. So with Vue, you have a library called vvalidate. And what you can do is you can pass in that schema to your form validation library. I believe also React Form Hooks handles the same thing. And then from there, it will also validate all our form data. So if you think of this in the way, if you create a schema that you can use to, for instance, for data you want to send to an API, and you follow the same kind of structure, you can use that then in your form data. So again, we can reuse it in multiple places. Or maybe we want to reuse the same schema, but instead we want to create a server route using Nitro. And in this case, we have our event handler, and we can use the helper read validated body. We pass in the event, and this will validate the body of our request against the schema. So we're using it in multiple places. Or we can generate data. So in this case, we have Zod schema faker, and we can pass in the user schema, and we can say, hey, create me a mock data based on this user schema. So, and then finally, if you want to now start using AI, and especially this nice library from Versal AI, if you want to create structured data using AI, you can use the same schema, pass it into the generate object method, and you can pass a prompt along, and it'll generate you AI data based on the schema. So you can quickly see, not only are we just creating a use case where we're validating data coming into an API, we're able to generate data because we're given instructions to our tooling saying, hey, this is the shape we want, and then it can provide us with those, that structured data. So there's lots of tooling support. I'm not going to mention them all. I will just show them to you briefly. So there's a lot of libraries that handle a lot of these schemas. So you can use different API frameworks or form libraries, UI frameworks. There's many HTTP clients, some utilities, and there's also some routing. So if you do routing within your application, you can validate certain parts. This is only a short list. I do recommend looking to standard schema or the Zod documentation for additional libraries that they support. So what are the key benefits? Well, by embracing schema validation, we can create truly bulletproof applications, and we can catch errors at our system boundaries. We can develop in confidence because we know exactly when and how our data will fail. We end up with a single source of truth, so we can make all our types schema-driven, and we can use all those schemas now throughout our application and have one single source of truth. So what's my recommendation for an adoption plan? First, I'll just start small. You can just introduce one schema to handle one very sensitive API in your application. Then you can look to maybe replace your all your types within your application with reusable schemas. These schemas can be broken apart and they can be merged together. I didn't cover all that in the presentation, but it does have the ability to do that. Secondly, I would look to validate all the boundaries of our application. So not only just checking APIs, also validate your environment variables coming into your application. Validate they're there, validate they're what you're expecting, and fail early. And fourthly, I would look to generate all the assets of your application. And what I mean by this is if you have a stub server or any kind of mocking, when you want to develop your application locally, you can also generate that from your schemas. So the key takeaways today is TypeScript is not alone. TypeScript alone is not enough. Runtime validation is essential. We need to validate all our trust boundaries throughout our application and prevent any kind of runtime errors that might occur. We need to, validation from schemas are incredibly powerful, and they provide a great TypeScript integration. And fourthly, increment this slowly into your application. You don't need to replace everything in your application at once. You can go bit by bit. That's been me. Thank you for listening. If you'd like to see any of the slides, I've also prepared a demo application on this QR code. So if you want to see how Zod works in practice, you can also clone the application, and there's also some resources as well. Thank you very much, and thank you for listening. Oi, oi, oi.